Okay, Assalamualaikum and hi everyone. So today I would like to discuss about chemical equilibrium. Subtopic 1 that is 6.1 dynamic equilibrium. Alright, so these are the things that you are going to learn. Alright. Okay, so first of all, explain the following terms. So which means in terms of definition, reversible reaction, dynamic equilibrium, law of mass action. And then state the characteristic of a system in equilibrium characteristic. Interpret the curve. Okay, interpret the curve of concentration and product against time for reversible reaction. Alright, so chemical reaction can be divided into two. Okay, that is irreversible reaction and reversible reaction. So what is irreversible reaction? So non-reversible reaction and only one direction in order to form product. Okay, meaning that from right turn, proceed to the product. Alright, so it's represented by using the chemical equation with unidirectional or forward arrow. This is the forward arrow. Okay, for example, okay, general formula, let's say A react with B, produce C and D. C and D is the products. Okay, example in daily life is combustion. Let's say methane gas. This methane gas is combust in excess of oxygen gas and it will convert into carbon dioxide and H2O. And then one more example is halogenation. Alright, so methane undergoes halogenation with chlorine. Okay, chlorine molecule with the presence of UV. UV here is ultraviolet. And one of the hydrogen atom in CH4 is substituted with chlorine atom. And it will produce CH3Cl, chloromethane, and hydrogen chloride. So for these two equations, it cannot reverse back to the right turn. Always forward reaction. Okay, next. What is reversible reaction? So this is a reaction which takes place in both forward and reverse direction. Okay. Alright, so it is represented by the chemical equation with bidirectional arrow. This is the arrow, bidirectional arrow. Alright, next example. Let's say I have A react with B. It will produce C and D. C and D react together and it will form back A and B. For example, like decomposition of NO gas. So 2 moles of NO gas decompose into nitrogen gas and oxygen gas. Okay, next, nitrogen gas and oxygen gas is react together and it will form back 2 moles of NO gas. Okay, so this is the example. Let's say for this one, use bidirectional arrow is this is correct arrow. So for the second here, this is not correct, incorrect. The arrow here incorrect. As for the third arrow here is actually this is for resonance structure, to show resonance structure. So remember, for reversible reaction, you have to use bidirectional arrow. Okay, next, for example, let's say N2O4 gas decomposed to become 2 mole of NO gas. So from NO to gas, it will react together and form back N2O4. So reaction 1, which refer to N2O4 produce 2 mole of NO2. And reaction 2, that is 2 mole of NO2 produce N2O4, happen at the same time because they are in the closed system. So usually for the reversible reaction occur in the closed system. Okay, and the forward reaction, which means from right turn to product, and reverse reaction from product to right turn occur at the same time. Okay, so this is what we call reversible reaction. Okay. Alright, next, equilibrium. Equilibrium is a state in which there are no observable changes as time goes by. So when we observe, there is no change in color. So which means the system is already achieved the equilibrium. So at equilibrium, what would happen? The concentration of the reactant and product remain constant over time. So it is constant, no change. Alright, so equilibrium is divided into two: physical equilibrium and chemical equilibrium. Alright, so for physical equilibrium, it involves physical change. Right, for example, like H2O liquid, water, right? So it convert into water vapor. And from water vapor, it will condense and form back H2O, liquid or water. So number of H2O molecule leaving is equal to the number of H2O gas molecule returning to liquid phase. Alright, so chemical equilibrium, so involve chemical change. For example, like N2O4 gas convert into NO2 gas. So we can see that reactant and product is not the same. Okay, but however for the phase here, it can be the same phase or it can be different phase. Right, so for physical change, the reactant and product still the same. The changes here is referred to the physical state, from liquid to gas, from gas to liquid. Alright, so for this experiment, N2O4, so when a certain amount of N2O4 actually exists in liquid, is placed into a sealed flask capped at 100 degree. So the liquid vaporized at boiling point of 21 degree, and the colorless gas, so N2O4 at the beginning is colorless, begin to turn pale brown. Pale brown here, it will form NO2 gas, but still in small amount. Okay, the color slowly darken, but after a few moments, no further color change can be seen, which means the system is already achieved the equilibrium because no observable change as the reaction continues. So, however, the concentration of N2O4 is not the same as concentration of NO2. So it's constant, which means there's no change. Okay, but doesn't mean that it should be the same. Right, so at the equilibrium, the rate of forward is equal to the rate of reverse. Alright, so this the example of physical equilibrium for H2O, water. Right, so okay, at the beginning, so H2O liquid, water, so it will undergoes vaporization. So it should be in closed container like this. Alright, so we can see that the level of the liquid is decreasing, which means some of the liquid water has vaporized into water vapor. Okay, alright, so after a while, amount of substance in the vapor state become constant. So, how that we can know that it become constant? We can refer to the level of the liquid is remain constant. Okay, does not change. Which means number of liquid that is vaporized into vapor is the same as the number of water vapor, okay, convert into liquid, or water vapor condense into liquid. So therefore, the level of liquid is remain unchanged. This shows that the system is already achieved the equilibrium. Alright, so as for equilibrium, okay, at the beginning, we can see that N2O4 is colorless, okay, in this tube. Okay, after a few moments, okay, so the tube become pale brown. So this means that some of NO2 will form. Okay, will form. Okay, and then after a few moments, color become dark brown to show that more NO2 have been formed. Okay, and then when further reaction continues here, we can see that the darkened brown has no change, which means the system is already achieved equilibrium. So for the N2O4, this is the reactant. So reactant concentration will decrease. Why? In order to form more concentration of NO2. Okay, but when the system reach equilibrium, okay, so the concentration of NO2 remain same as the concentration of N2O4 remains. So we can see a constant line here. Okay. However, the reaction does not stop. Okay, still occur, and we can see there is no changes in the concentration of the reactant and product. So the system has reached equilibrium at this T. Okay, this T. Okay, in form of rate, graph of rate versus time. So we can see that when the system achieves equilibrium at this T, right, the rate of forward and rate of reverse is equal. So we can see that a constant line here. Okay, constant line here to show rate of forward is equal to rate of reverse. Okay, next. Alright, so what we already learned. So we already learned about reversible reaction. That is reaction which take place both forward and reverse direction. We already learned about equilibrium, that is referred to the state in which there are no observable changes as time goes by. How do we know that the system is at equilibrium? So these are the characteristics of a system at equilibrium. First, the reaction and product concentration are constant over time. So we can see in graph of concentration over time, the line for product and the concentration and the reactant become constant. Constant, no change. Forward reaction rate is equal to the reverse reaction rate. Okay. And the reaction quotient Q is equals to equilibrium constant K. Alright, so what are the relationship, okay, between the reversible reaction and the equilibrium? Okay, if these two combine together, and it will form dynamic equilibrium. So what is the meaning by dynamic equilibrium? So it occurs when the rates of forward and reverse reaction in a chemical reaction are equal. And reactant and product concentration stop changing, become constant. Because they are forward and reverse rate become equal. Alright, so for example, like this analogy in our daily life. So the rate of water inflow is equal to the rate of water outflow. Okay, and then we can see the level of the water is constant within the bucket, which means the system is already achieved equilibrium. So I think everyone has an experience while moving upwards using escalator. Right, so girl moving upward at a speed v. Okay, same thing goes to escalator moving downward at speed v. So the system is already achieved equilibrium where the speed is equal. Speed of forward and speed of downward is equal. Alright, so now we move to these two graphs. So there are two different graphs here according to this equation. The first graph is referred to the concentration against time. Okay, as for the products here, as for the reactant here, the reactant it will decrease. So, and then for the reactant will decrease. Okay, as for the product, it will increase. Okay. Alright. So at T1 here, what happened at T1? So we can see that the concentration of NO2 does not change, become constant. Same thing goes to N2O4. The concentration does not change, become constant. So meaning that the system is already achieved a dynamic equilibrium. So the reaction still occur, does not stop. However, the concentration of product and reactant is constant. Okay, in terms of rate against time, so for the rate when the system is already achieved equilibrium at T1, we can see that the rate of forward and rate of reverse is equal. So we can see a constant line here. Okay. Alright, so next, this is an example of a graph. Okay, graph of concentration against time. So there are three cases. The first case is start with NO2. Alright, so from this equation, so at the right side, at the left side, okay, this is referred to the reactant. at the right side, this is refer to the products. This is the product. So for the first case, it start with NO2, which means it start with the products. So we can see that. So the amount of NO2 is 0.2 molar. Okay, somewhere here. As for N2O4, it's 0 because not formed yet. Alright, so when the reaction occur and achieve equilibrium, okay, the concentration of the NO2, it will decrease because it start with NO2. Okay, and the concentration of N2O4, it will increase. Okay, so at equilibrium here, alright, so we can see that concentration of NO2 has dropped into 0.024 here. As for the concentration of reactant, okay, reactant N2O4, this is the reactant here. So it increased 0.0898 somewhere here. And then it remain constant when the time goes by. Okay, so which means the system is achieve equilibrium. Okay, for case number 2, it start with N2O4, which refer to the reactant. You start with N2O4, which means the reactant. So we can see the initial concentration of N2O4 is 0.67, somewhere here, up here. And then it will decrease. So at the beginning, concentration for the NO2, which refer to the product, start with 0, not formed yet. And then it will increase. Okay, at this T time here, at equilibrium, when equilibrium is reached, we can see that concentration N2O4 at equilibrium becomes 0.643. And the concentration of NO2 at equilibrium becomes 0.0547. And when the reaction continuous, so the concentration of NO2 and concentration N2O4 remain unchanged, become constant. Okay, right. For case number 3, it start with NO2 and N2O4. So there are 3 sample data here, right? So this is the initial concentration for N2O4 and initial concentration for NO2. And then when reach equilibrium, okay, and the concentration remain constant. Okay. So meaning that at equilibrium, the reaction does not stop. Therefore, the rate of forward reaction is equal to the rate of reverse. Even though equilibrium is reached in all cases, the equilibrium concentration of NO2 and N2O4 are not the same. Tengok, it's not the same. Not the same. But it's constant. Okay, alright. So, and then one more thing, when we write the K values, when we calculate, the K value become constant. Okay, 4.6 times 10 power of negative 3 to show that the system is already achieved equilibrium. Alright, so I have one question here that we can try. Okay, right. So, consider 3 mole of O2, okay, produce 2 mole of O3 ozone gas. In one experiment, 5 mole of O2 was introduced in closed 2 little vessel. Okay, at equilibrium, the number of mole of 2 has dropped by 2.5 moles. Okay, while 4 moles of O3 was produced after 18 seconds. Sketch and label graph of reactant and product concentration against time. Alright, so because it's referring to the concentration, so first of all, you have to calculate the initial concentration. Okay. Alright, so we start with concentration of O2. Initial 2.5 molar. Okay, and then concentration of O2 at equilibrium. Okay, equilibrium is mentioned here is drop by. Okay, so drop by means given here is refer to the changes in mole. So which means this is not equal to the mole at equilibrium. So you have to calculate. So initial mole is 5 minus 2.5 moles. So we get here 1.25 molar. Alright, next concentration of O3 at equilibrium 2.0 molar. So for the initial concentration of O3, initial is equal to 0 because not formed yet. So the reaction start from oxygen gas. Right, now we want to sketch the graph. So first of all, you have to draw the y-axis and label concentration. Okay, and with the unit, there is molar. Right, next, x-axis time. Okay, in the question given to you, 80 seconds. So unit here is second. Right now, so we plot the graph. Draw a line here to show the time at equilibrium, which equal to 18. Of oxygen is 2.5, and it will decrease to here, somewhere here. Okay, draw a curve here, and then constant line. Okay, next, from 0, now we come 2.0 somewhere here. And don't forget to label, this is O3, and this is concentration of O2. And then one more thing that you have to label here is this one, at equilibrium. Alright, next question. Okay, so how many marks that you will get here? So first, axis here, 1 mark. And then each of the calculation, 1 mark. Okay, and then the curve for 2 marks. One for O2, the other one for O3. And then label equilibrium, label 18, label this. So 1 more mark. So these are the maximum mark that you can get from this question. Alright, next question. Alright. Okay, so for this question, actually this is tutorial question. Alright, so nitrogen 4 dioxide dimerite as follows. 2 mole of NO2 gas produced and 2O4 gas. Sketch graph showing how the concentration of reactant and product above vary. Meaning that difference during the course of reaction. Alright, so meaning that for this one, since there are no data given here, so we just draw a general graph lah. General graph. So this one label concentration. The unit should be molar. Okay, and then x-axis is time. Usually time here is in second. Alright, so we know that the concentration of the reactant here, it will decrease. So decrease and then become constant. Okay, and then label, this is for referring to NO2. As for the concentration of the products, it will increase and become constant. And label, this is N2O4. And lastly, don't forget to draw here dotted line to show the T and time that is the equation reach equilibrium. Right, and then label at equilibrium. Okay, how many marks that you can get here from this sketch? Axis, 1 mark. Okay, and then we have a curve. There are 2 curves here, 2 marks. And then you label, label T, and then label at equilibrium. You get another 1 more marks.